Okay, guys, I think I'm start recording here. And chapter one. Chapter one will go over the material, the basic knowledge of chemistry, as you will see, and we'll start off looking at a problem. Every day you watch a problem, and then you look at this problem, and you can make out of this. We make out of this a problem. First, you'll make an observation of this problem, and that will start covering the something called scientific method. I might differ from whatever you have here inside the PowerPoint, but this at the end is the same thing. So here it is. So we'll start. If you look at the scientific method here, yeah, the scientific method is. I will start first of all making an observation. So I'll start with this one here. Maybe make it thicker here. I'll start with this one here first. Observation. I observe and uh, anything happened in nature, and then make a note out of this. So, and after that, after my observation, I'll make a statement. This statement here, I call it hypothesis. Hypothesis meaning just a statement based on actual observation. This statement might be true and might be not true, might be wrong. So, therefore, I go from observation, I make hypothesis. Now, as I said, this statement, I have to prove it first, whether it's correct or wrong. So I go and make what? Experiment. Okay. And this experiment, I have to collect data. This is quantitative analysis. Now, my observation at the beginning, that's qualitative analysis. But qualitative analysis means there is no quantity there, so it does not have that much of weight. I have to do an actual experiment to see how is my data supporting this statement or rejecting this statement. So this is number one, this is number two, this is number three. Again, this is connected to the qualitative analysis, which is based on my just observation, just pure observation. That's qualitative. But again, qualitative is not helping me that much. I have to do the actual qualitative analysis or testing this by experiment. So, and that's what experiment and analysis, those are together, number three. And then after that, after testing, I ask other scientists all over the globe to help me if with this type of observation, with this type of data I got, with this type of conditions of the experiments I have done, are they getting the same thing I'm getting? If the answer is yes, and that's proven to be true by many scientists over the globe, then I can, with certain position, say to the scientific community, this can be elevated from just normal statements, normal hypothesis, to a theory. Okay? This theory then, so from this analysis here, from those three here, goes to something called, I make a theory here. With the help of the scientists, they test everything. It looks like my statement is true. Correct? Now, through the years then, through many years, many scientists, they have to test this theory here. This theory, correct, might be changing depending what technology is available, whatever is conditions is available. So, but the statement in general, the theory is correct. Now, I can elevate this theory to scientific law after a while. So after a while, after the help from many scientists with all over the globe and different conditions, and it has to be for years. Not you cannot take just a theory one day or two or 1 year or two and make them scientific law. That will not work. That will not work. You have to prove this theory is really real. It's not really affected with, by other circumstances, by other conditions, and by other technologies, whatever. Therefore, I can say with certainty that this is a theory and is sticking there and standing by itself. So this is a scientific law. Usually, scientific law is very hard and very rare to be changed. Regardless, whatever technology, whatever advances we made, scientific law is scientific law. It stays there. And we have hundreds of years scientific laws in chemistry, and especially in chemistry, physics. Um, uh, it's not changing. They are the same. Other sciences like biology, they have more advances in technology. So you'll see evolving. So this law might be not solid, might be always evolving. And as you say, the microbiology, DNA, all those sciences in biology, they are really evolving. So you'll see a lot of stuff going. It's not really per se. It's like physics and chemistry. Those are solidified laws, and they stayed for years now. So a textbook of chemistry is not changed for over 60 years, content-wise, scientific law-wise. So what's really changing is just the images and the pictures. They are changing inside the textbooks. Are you following me? So the scientific laws, they remain there. So now we can just recap the whole thing together and make a conclusion. So I looked at some stuff, some whatever phenomena there outside, and looked at them and then said, well, I can make a statement based on my observation. This statement is called hypothesis. Might be correct, might be wrong. I don't know. And that's what I made of observation. That's called qualitative analysis. I analyzed, I looked at the whole thing, and then made a statement. Qualitative. It's not really qualitative. I don't have anything handy or anything in my hand to prove that's really true. So I go to the lab. I do the experiment. And with this data, then I can test if my statement, the hypothesis, is true or is not true. It came out to be true, but still I'm shaky. So that's what my finding, correct? I have to seek help by the other scientists all over the world, asking them to really verify what my findings are, and if they are agree with that or not. If they are really agreeing on this, they said, yes, now your statement can be theory, and we will test it even further. Again, you cannot take the theory to the law within 1 year or two. It takes years. It takes a lot of efforts throughout the globe, throughout the whole world and the whole scientific community to agree on a scientific law after a lot. Because theory can changing. As I said, that's what's happened in biology. Biology is a very fluid science with a lot of advancements, a lot of everything new in biology. It's not like in chemistry or physics. We have a lot of new items, new things, new compounds, but not compared with biology, because there's no limit there in biology, because everything is because they couple technology and biology. You can hear there's some areas of technology of DNA or technology of a cell or whatever, and all those diseases you have, all those type of cancers, all that, this is evolving. Those are things are evolving. So biology is no limit. Therefore, the theory will remain there for a long time to be a scientific law, correct? While chemistry and physics, the scientific law stays, and it will not take that many years to take the theory up, elevate it to scientific law. Any other question you have about this? Make sense? Start observing. That's your qualitative analysis. You make a statement. That's your hypothesis. You get this whole statement inside the lab. That's your qualitative analysis. Beside your qualitative analysis, you make out of this a theory by yourself, of course, but it's not a theory yet. You have to seek other people's opinion and feedback. If they get the same thing at the same condition, then you said, yes, this is a theory. Now we have to elevate it further to a law. Let's do the whole thing in this area for many years by different scientific communities, and within 5, 6 years, whatever, 6, 7 years, we are getting with different technology the same results with different conditions and technologies. This is it. That's just the law. That's scientific law, correct? So scientific law cannot be rejected. That's a scientific law because it came an effort of many years and many scientists and many scientific communities. It's not by one person or two or three. Are you following me here? So, and it's not changing. And that's typical for physics and chemistry. We are compared with biology. We have limited of advancement compared with biology. They have unlimited advancement, as you see. Every day we learn some diseases coming out there, correct? Especially in the cancer area. I mean, it's unlimited area of advancement and technology and research there. So that's what the first case, how you go for the approaching scientific method. That's the way we are approaching scientific method, scientific procedure, or any observation we make. So any observation you make, you can follow the steps of scientific method. So, any question you have? Any question? Raise your hand. Don't be shy. So, don't be shy. So, and your voice will not be recorded because you are far away from the speaker here. The speakers are not here. They are all the way at the corner. So, not so. But ask questions. So this is the first thing here. I will take this one here out. And this is a requirement math skills in the chapter. We have to make it because that's a requirement for the department. But I'm not going there because I remember those are about 8, 9 grade. Those are 9th grade level. Everybody agrees on me? And I remember for my kids when they were kids, they're grown out now. So, but that's 9 grade type of math. So if you have any problem with it, you forgot about this. I have older students here, and they forget about this. They can come to me, and then we'll go through this together. Okay, guys. So if you forget about the log rules and everything and the exponents, don't be shy. We can make an WebEx meeting and then we can go over that together. But I'm not spending time on that because that's just, and this is here the math skills and how you take this. Make a slope, you make a linear relationship between y and x. So, but that's for you here. Now, let's go for another topic here, which is very important here. We'll talk about matters, the matter itself, definition of a matter, and we'll talk about what type of matter we have, and then how to mix those type of matters together, what we are getting out. So, the definition of a matter here first. anything that has a mass and has a volume, occupies a space. Anything occupies space and has a mass is what? It's called the matter. Now, if I talked about matter, how about the antimatter? What is antimatter? I know anti means the opposite, correct? So if I speak about matter having mass and volume, then what's the antimatter will have? No mass and what's that? We have what? We have Halloween coming soon. Ghosts. Halloween is coming soon, correct? Can ghosts go through the wall? Yes. But me, I would be bouncing. I would be my head would be damaged, correct? So I cannot go through. I have a mass. I occupy space. So I cannot go through the wall. Can I? No. Can X-ray go through the wall? Can gamma ray go through the wall? Because they have no mass, correct? And they don't occupy any space. That's the X-ray gamma ray. That's an example. But we can, because we are approaching October, a couple months, end of October, 31st of October, this Halloween. We'll have activity, by the way. We'll have an activity outside in front of the end building. But anyway, you can go through, the ghosts can't go through the wall, correct? Because the wall, that we call ghosts are antimatter. They have no mass and they cannot occupy any space. So that anytime you have a matter, you have to think about there is antimatter. Now, suppose the ghost is just a made up stuff, but we have a ghost called gamma rays, correct? X-rays, you can see your bones. So the X-ray go through your body, through your bone, cannot go through some area for the bones. So the bones are not attacked by the X-ray. X-ray cannot go to, it can go to depth, but not. Through the whole body, yes. Tissues, yes. But the bones are not. Gamma does. Gamma ray or radiation do go through the bones. And those very dangerous radiation. But X-ray will go through all your body except the bones. So all the body is the bones will appear, it's not attacked by the X-ray, so they will appear in the negative, in the microfilm. Are you following me here? So that's anytime. So X-ray between a ghost and non-ghost. So it does not have a mass, but it does not have the ability to go through. So it looks like it does have some effect because not all the rays are going through. So we have alpha, beta. When it comes to nuclear chemistry, alpha, beta, gamma. Alpha, beta, they can penetrate through, but not deep inside. They cannot go through. So if I'm working with alpha and beta inside the lab coat will be enough because they cannot go through my body. Correct? As I speak here in the sun, we have a lot of alpha and beta radiations. Yes. Good morning. So now we spoke about matter and matter. And the type of matter we have here, gas, liquid, solid. Do we have a fourth one? What? I heard the right answer? Plasma. Okay, we don't add plasma as a fourth type of matter. So we have gas, solid, liquid, and gases, and plasma. What is plasma? What is plasma? Somebody will tell me what's plasma? What's that? Yeah. What's that? Yes, that's correct. So therefore, we don't add it. It's a gas. It's argon here. Give you that color. If you have xenon, it will be purple. Did you see the purple light? You see the purple light outside some stores? Purple, red, all those are colors from ionization. So a gas that be bombarded by extreme condition of high voltage can be excited and ionized. So a charged gas called plasma. Therefore, we cannot add it as per se a new matter because it's really gas. So it's just advanced type of gas. By ionizing it, you get a plasma and photons that the color there. Are you following me here? So, but if you look at the whole thing, we have really 4 states of matter. We have liquid, solid, gas. Now, the unique about the solids, as you see, it does not really matter of where you put the solid. So it's not dependent on the shape of the container, correct? It has a very compact, the molecules are very compact together, correct? And therefore, the electricity conduction is very, very high, and it's not compressed. You cannot compress a solid. If I put a lot of pressure on this desk here made of, say, plastic and wood, what will happen? If I put my lot of pressure on this, what will happen? It will break, correct? It will break. But if I have liquid and gases, if I compress them, what will happen? If I compress, put a lot of pressure on the liquid, what will happen to the liquid? What's that? Now, will be crystals. Have you seen solid crystals of oxygen? No. So if you press oxygen too much, you make out of it a very pale blue liquid. Compress it, put it a lot of high pressure compressors, you make out of it solid crystals. Now, what you can see in the fire extinguisher, this white powder. What is this white powder? Come on, don't let me down. White powder from the fire extinguisher. What is that? That's a gas, liquid, or solid? That's a solid because it's powder, correct? But it appears. You suffocate somebody with it. If you push it on somebody else's face, that somebody will be suffocated and might die, correct? Why? What is this? What's this white powder inside fire extinguisher? Come on, don't let me down. You buy it from the farm market, from any grocery or even gas station. Dry ice, CO2 gas. So if I have a gas here, some gases, they don't go liquid. So they don't go for liquid. So if you compress it, they don't go for liquid. If I have a gas here, and I compress it, put it on a lot of pressure, I make out of it dry ice, solid. Dry ice, correct? How about take the dry ice, put it even, compress it further. I make what? The white powder in the fire extinguisher. Make sense? Make sense? And the fire extinguisher, what really is combustion is a fire, chemical combustion. Fire means you have a matter and you have a pure oxygen. You bring them together, you get fire. That's fire. The word fire is a chemical reaction between pure oxygen and a matter, whatever type of matter. So you combust this material by you go above its ignition point with pure oxygen. If you eliminate oxygen, correct, what will happen? There will be no fire. Therefore, if you have a fire at home, do not add to it H2O to get it down. That's wrong. Why is wrong? The fire is about 600 degrees. You put H2O, it boils at 100 degrees, correct? So the H2O will be boiling, taking the fire, spreading the fire all over the place. The pieces of the whatever is burning. Are you following me here? The best thing is cover it. Bring a big thick blanket and put it on the top of it. Eliminate oxygen. The fire will go down. Can somebody smoke on the moon? Can somebody ignite a fire inside the moon? Why? There's no oxygen. It's the same concept. Make sense? It's the same concept. So if you have a fire at home, I have a fire extinguisher. My wife is scared to use it, but it's very simple. It's not really difficult to use it. The main thing is go to the center of the fire. So you look at this. This is a fire here. Look at the bottom of this has to be in the center of it. On the Ph.D. requirement, we have to take class with the fire department. It was in the Colorado, it's about 30 years something. You have to take a class for fire, how to fight fire, and you have to pass this. There is no grade, pass or fail, and then you have to repeat the class again to get to get approved by the fire department, because you'll be instructor inside the lab and you have to know how to fight fire. But anyway, it's not difficult to manage the fire extinguisher, and most of it is carbon dioxide we use. We have other types. We have H2O, tap water with the high pressure, steam, and we have chemicals. Those are special. But all in the labs, we have all in all at home or the fire, they have CO2, mostly CO2 powder. That's the powder you have. Okay, guys. So we can go from one state to another state, correct? That's a physical change. We'll come back and look at this. So what's unique about gas and liquid, both of them, they take the shape of the container. If you look at the whole thing, they take the shape of the container. Liquids and gases take solids not. And the other thing about liquids, they are relatively coming closer, not close like a solid. In the molecules come very close to each other, correct? And they are not randomly organized. They are really very nice organized and closer to each other, but not that close like a solid. Gases, on the other hand, take the volume of and the shape, correct? Take the volume and the shape of the container, and the molecules are randomly spread out all the place. So I have air is made of what? About what? Mostly what? Nitrogen, correct? About 75% nitrogen, 24% something is oxygen, and the rest is inert gases and carbon dioxide. And humidity, H2O. But anyway, so can I pinpoint where the oxygen is, where the nitrogen in the air? Even if you look at them, you have a picture of them, you cannot, because they are moving around speed of light. You cannot pinpoint where is oxygen, where is nitrogen molecules are. You cannot. So that's typical of gases. The liquids are very close of behavior of gases, but they are coming a little bit more structure, more organization than the gases themselves. And we say the conduction of electricity, solids are the highest conductor, gases are isolator, and the liquids can act in between. So liquids are in general semiconductor, not 100% conducting electricity, not isolating, not non-conducting. So they are conducting electricity, but to some extent. So if somebody here, I will talk about this later on, but somebody gets electricity in his or her body and has whatever filled with the whole area, it's gas, the gas will prevent that person to be electrocuted 100%. Gases are not conducting electricity. If the gases are conducting electricity, there will be no life on this earth from humans. We'll be working like zombies because you'll be electrocuted, correct? That's not the case. That's not happening. However, solids are the highest conductors of electricity. Liquid in between. That's for the conduction of electricity between the three types. The second number, compressibility. Compressibility, you put pressure on them. Solids are not compressible. If you put pressure on them, you break them. Liquids, if you compress them, yes, you can make out of them what? Solids, correct? Gases, you can make out of them solids, but they go through liquids. But some of the gases, they are not going through liquids. So usually you come solid first, here it is, solid goes to liquid, to liquid, goes to gas. Thus, the majority of matter are types. They are going through this liquid, so a solid, liquid, gas. However, some compounds, some matter, they don't go liquid. Some of them is CO2 gas. There is no liquid CO2. Are you following me here? If you compress CO2 gas, you make out of it what? Dry ice. If you keep the dry ice for a couple, less than 1 hour, it will evaporate. There's no liquid there, correct? But if you compress the dry ice further, you make out of it white powder. That's what in the fire extinguisher. Some other, did you see mothballs? Did you smell them? They smell very, very distinct. Mothballs, they are used to kill insects inside the kitchen, whatever. They are put inside the kitchen mostly, or outside the backyard to kill out those insects. So mothballs are the same thing. Naphthalene. Naphthalene, if you put one ball here, after a couple hours, you see it in the ceiling of the room. So I have a couple of mothballs here. In a couple hours, they all disappear. They don't go because they go by warm, the heat of the place enough to evaporate them. They sublime. So CO2 sublimes, but most of the matter, they don't sublime. They go through liquid and then the gas. Are you following me here? Now, and the plasma, as I said, we can't really consider it as a matter itself because it is a gas. Plasma, it is a gas, but under extreme conditions. Correct? Any question you have? Now, there is a FET simulation. You can try it at home, and then you can look how you can, I mean, with this, give you the idea of the difference between those three type of matter: gas, liquid, and solid. Okay, guys? So, and that's what we have just covered, whatever we said now. Now, let's look at the matter itself. So now we have the matter, types of matter: solid goes to liquid to the gas. Majority of matter will go this way. Some matters will not go through liquid. They don't have liquid phase. They go from solid to gas. Or when you compress them, they come back from gas to solid. Correct? So, and there are some types of the matter itself. We can recognize those pure substances and mixtures. So the matter itself of solid, liquid, gas, they can be pure substances and they can be mixtures. So what's the difference between pure substance and the mixtures? Really, mixtures are made of pure substances. The pure substances is type of matter combined together with specific composition, fixed specific composition, thus make them as a pure substance. There's nothing there. So the pure substance, they have their own characteristics, not shared by any other pure substances. So it has to be fixed composition and distinct fixed composition there. That's a pure matter, the definition of pure matter. And the pure substance. The pure substance can be element, can be divided into element, correct? And can be a compound, correct? So now we have pure substances. We have pure substances can be element and can be compound. Now, if I look at this, I will say can be molecules, correct? Now let's see here. Let's open Word here. Okay, I'm opening Word here and then just go through this together here. just to make the definition that everybody is not confused. A lot of students are confused. So we have matter. Can you see it? Yeah, we have matter here. Out of this matter, we have solids, liquids, and we have gases, correct? So we have out of these three, we have pure substances, and they have to have fixed matter with fixed compositions, with fixed composition. And we have mixtures. Now, mixtures are combination of two pure substances or more, correct? So mixtures is combination of two or more pure substances. So now from pure substances we can, let me go and maybe change the color here. Pure substances, I can recognize two items here. Elements, okay, and I can designate another type called compound or molecule. And for the mixture here, I can designate two types again. Homogeneous mixture and heterogeneous mixture. Okay, so can element go further? Yes, element can be made of small tiny units that cannot be broken further by any chemical means or chemical reaction. Those are electrons, protons, and neutrons. Those are, so the elements are made of the small tiny units called the atoms. All this here, atoms. Elements made of atoms, and those atoms they cannot be broken by chemical means. They can be broken by nuclear means, by nuclear reaction, but not by chemical reaction, correct? And the atoms are made of electrons, protons, and neutrons. Now the compound and molecules are combination of elements, two or more elements. So compound and molecules, combination of two elements or more. With fixed composition. Fixed composition means whether you are here or you are in the moon or you are in the North Pole or South Pole, wherever you are, any spot in the universe, our galaxy called what? The Milky Way, correct? Any galaxy you are in, the composition is not changing. That's we call this one here. We call this one a compound, meaning or molecule is not changing. So, what is the difference between molecule and compound? Somebody will tell me here. Somebody will have. Can I take this one here out? Can I take this one out? Okay, I'll take it out, and you have everything inside the PowerPoint. So now we are looking. We said, look one at a time here. We have element, and we said the element is made of small tiny unit called atom. It cannot be broken in small units by chemical means, but by nuclear means, yes. And these atoms are made of electrons. This is E minus, protons, P plus, and neutrons. I use just the first alphabet, 0, no charge. So that's the element. And then we have a compound and molecule. They are the same, but there is a difference between them. So the molecule is the smallest fixed ratio or composition, the smallest fixed. So molecule is smallest ratio of the elements. Here, this has not to be the small sphere's largest ratio of the elements. So, for example, let's put here an example here, and let's put here an example and say I have CO2. This is a molecule or a compound? Carbon. So carbon to oxygen is 1 to 2. This is smallest ratio or larger ratio? What do you think? Smallest ratio, correct? So this is small. So we call CO2 is molecule. Correct? Nitrogen gas, N2. So N to N, 1 to 1. So this is what? Molecule, correct? Now let's look at another example. Let's show you what's the difference. Smallest units are compound. But this is a combination of two elements or more. That will be a molecule or compound. How differentiate between compound and molecule? By looking at the ratio between the elements. If the ratio is the smallest one, this is a molecule. If larger than this is, it's not small, but larger one, that's a compound. I'll show you here an example. Can I take this one out? Everybody has it? Everybody has it? Okay. So let's take out and look at one of the examples here. Let's take here. So I have here B2O3, B2O5, and then B4O10. And then you are asked, what is really a real molecule? What is a real compound out of this? From us looking at this is the highest. So this one cannot be molecule. This one is a compound. Correct? Why? Because phosphorus to oxygen ratio, this is 4 to 10. That's very large, correct? So this is the smallest one between them. There's the oxide of phosphorus. So this is the smallest one, 2 to 3. So small, or smallest one ratio. So this is a molecule. Correct? This one here, look at this, and that's what's happened for most of the textbooks. If you read the publishers, here is the textbook here. This one, I can say 2 to 5 is not that small, it's not that big. Because I know the biggest one is here. The smallest one is here. So this one sometimes swap between a molecule and a compound. And you will see that in the textbook of a lot of publishers, authors, they don't really define. They swap between molecules and compound, and they don't use distinction. Some very good authors, professors, in their writing of their textbook, they really make distinguish. They make a distinguish points between those two. And if they have, like this case here, they can use a molecule or compound because this is not small, not big. Correct? Are you following me here? And that's you can do all this stuff here. How about H2O? This is a molecule or compound? What do you think? What do you think? That's small, 2 to 1. That's a molecule. But how about H2, hydrogen peroxide? That's what? 2 to 2. So that's not that big, though, correct? So you can't swap it between molecule or compound. You'll see textbook, hydrogen peroxide, sometimes called molecule, sometimes called compound. Are you following me? That's not in the PowerPoint. That's not your eBook. That's coming from experience. So when you read that somebody else's work, then you can tell. But that's a good textbook will make a distinguish points between those two. Smallest ratio, that's a molecule. Smallest, ever smallest. In medium in between, you can swap. This can be molecule, can be compound, correct? So now we went through this and we went through atoms. Atoms is the smallest unit. And the word atom is a Greek atom, means the smallest unit. That's the way it is. And it can be further, it can be broken in small pieces by chemical means. But if you bombard an atom with the neutrons or whatever radiation you have, or protons, you can break the atom in small pieces. So that's nuclear reaction, not chemical. Chemical reaction cannot break an atom. So that's it. So let's go for mixtures. I want to see the mixtures, how the mixtures are doing. Any questions so far about this? That will not come in the exam or quiz, but at least whenever you read anything about chemicals, if the ratio is small, that will be molecule. If it is large, that will be compound. If in between, not large, not small, you can swap between both, molecule or compound. So, done? Okay, let's go for the mixtures now. I'm switching colors because I want to keep you awake, because that's the way this, what I read about this, to keep the students awake, just keep changing the colors. So that's what, that might work to some students, yeah. So anyway, so let's look at the mixtures here we have. We have a homogeneous, and we have heterogeneous. It's here, so. Okay, so homogeneous and heterogeneous. What's the difference between them is just by looking at them. If you have two layers here, correct, or two phases, that's heterogeneous. If one single layer or phase, that's homogeneous. But the definition of this is when you mix those pure substances, if the mixing or the distribution of those pure substances is fixed throughout, the mixing procedure, this is homogeneous because you can see one single layer. If it's not fixed throughout, and you can see more, you will see two layers or more depending how many pure substance you have. And as you will see later on, this one has to do with the polarity of the solution. So it will depend on the polarity of the solutions. This one here will depend on the polarity of the solutions as well. So As you see later on, if the mixture is made of two substances and they have the same polarity here, so they will make the distribution of those compounds or molecules inside this mixture is fixed, correct, throughout the mixing. But if it's not, they are not the same polarity, here. We'll come later on in other chapters. We'll talk about the polarity, what does polarity mean later on. But at least you will know that the mixtures are made because of the similar polarities, that's homogeneous, different polarities, that's heterogeneous. And the heterogeneous, you can see two layers, correct? For example, I mix sugar and the tap water together. That's homogeneous or heterogeneous? Sugar and H2O. Heterogeneous? Sugar is polar, correct? And H2O is polar. That's similar polarity, so they have to be what? Homogeneous, because when you solve them, you can see only one layer, H2O. You don't see the sugar anymore, correct? You don't see the sugar. With the assumption you don't use too much of the sugar. If you use too much of the sugar, some of the sugar will settle down at the bottom. Then you have a supersaturated solution. That's not what we say. So, different polarities. Well, if I have mixing oil, if you mix oil with H2O, oils are not soluble in H2O, correct? And they are less dense, so they will float, correct? You can see it at home. Give a couple drops of H2O and a couple drops of oil, you will see the oil is floating on the top of H2O. The floating is because it's less dense. Density is not the same. So less dense. Oils are less dense than H2O, so they will float. But they are not mixed. They are not mixing together. So therefore, we have heterogeneous mixture. Correct, guys? Any question you have? We'll go back to our. Any question? So we'll go through we covered this one here, and you can look at this one phase as here it is. Let's see here. One phase. This is what? Homogeneous or heterogeneous? This is what? Homogeneous. And this one here, two phases, heterogeneous. This is solid at the bottom, so if you add too much of a sugar and less H2O, so the sugar would come and then will be at the bottom. It's not soluble. You exceed the maximum solubility of H2O as a solvent, therefore you have supersaturated solution. Correct? So, and this is the pure substance, can be element. That's a copper. Copper wires are copper element, and they can be compound, whatever can be compounded. This is just, I think it's a blackboard, correct? What is this? A blackboard, or made of polymer? Okay, so that's a pure substance. So we'll go here further. Okay, so now physical and chemical changes. So with this one here, we have to know keywords. How I can determine this is a physical change or physical property. I can determine this is a chemical property or chemical change. Well, there is keywords. So if physical change, then I have to have something called observe. I have to have a keyword called observe. You are observing things, correct? But the chemical change here, it has to be carried out. You do actual experiment with that. So you do what? Actual experiment. Those are the keywords. If you have the definition Anything observed, that has to be physical. Anything is carried out, that's what that's that's a chemical. So let's do this one here, and here it is. Physical is the properties observed. That's the key word here. Without changing the composition, and that's the another key word is you don't change the composition of a matter in a physical change. But in the chemical change, I mean, you have in the physical change, you can recover the matter itself. Recover the matter itself. Here is, I mean, reversible. They call it reversible. So reversible. So the chemical change is irreversible or not reversible. Okay, guys, we have 4 minutes. We can see some worksheets to look into worksheets here. And let me see. Let me take this one out. And I want to see a worksheet here for physical and then we'll come back in. So here, guys, look at that and tell me. We'll do this one here. Let's do this one here. We'll do, we have still 3 minutes. So identify, by identifying here, C, chemical, P, physical. Blue color is physical or chemical property. That's a property because the property is means physical. This is a physical property. You have not done anything change. Change, you have to carry out a change. Carry out to the sum. So blue color is what? Physical. Okay, correct. How about density? Density ratio between mass over the volume. Mass over the volume is what? It's physical, correct? Each compound has its own density. Flammability, burning. Burning, that's a combustion reaction with oxygen. Because if you have a piece of wood, you cannot get anything after the burning. Everything is gone. Everything is ashes, correct? So therefore, it's not reversible. You cannot get things back. So this is chemical. So we have still 2 minutes. Cool yourself down now. Cool yourself down. 2 minutes. Solubility. No. When you dissolve sugar inside H2O, can you recover sugar back? Yes, by evaporating the H2O. Correct? Is the sugar is changing in composition? No. H2O is changing composition? No. So solubility is a physical characteristic or property of a matter. This compound is soluble, this compound is not soluble. So, reacts with acid. React with acid. Chemical. Okay. Support combustion. The combustion is a chemical reaction, correct? It's pure oxygen. That's a chemical. And the taste is sour or bad. So what's that? What's that? That's a chemical because that's anything with the smelling bad that's coming from what? The chemical reaction. And we have H2S inside our body. After we eat, we generate this. And if you have very bad food, then you get, that's called farting gas. It smells very bad. That's a farting gas coming out. Any reaction. That's a chemical reaction. When we come back, we'll go through this again with a lot of examples of this.